Alright, let's do page 2. It says differentiate this, which is a quotient, so I have to use the quotient rule. F prime of x would be the derivative of the numerator. We want to do the derivative of the numerator first because there we have to do a subtraction. It makes a difference which one we do first. So the derivative of the numerator, which is 2, times the denominator, 5x plus e to the x, minus the derivative of the denominator, which is 5 plus e to the x, times the numerator, 2x minus 9. Get used to using parentheses. Over the denominator, 5x plus e to the x squared. And that's the quotient rule. Now let's do a little simplification. So we get 10x plus 2e to the x. And then we're going to have to subtract all of this. So I'm going to put a subtract, and it's going to be all 4 of these terms. 10x. That's going to be, I'm forgetting the minus for now. 5 times negative 9 is negative 45. Plus 2x e to the x minus 9e to the x over 5x plus e to the x quantity squared, which would be, now I can distribute that minus, which makes that 10x be negative 10x plus 45 minus 2 plus 9, and so now I get 10x minus 10x, they're gone. I got 2e to the x minus 2x e to the x, so they don't cancel. Plus 9e to the x, that's 11 e to the x, minus 2x e to the x, and then plus 45 over 5x plus e to the x squared. Number 5. Find the derivative of cosine x times sine x. So that's a product rule. So I'm going to have to do the derivative of cosine x, which is negative sine x times sine 2x plus the derivative of the second, so that's going to be cosine 2x times the derivative of 2x, which is 2, using the chain rule on that, times the first. And that's all I really need to do. This one won't clean up very well, so we'll just leave it like that. Now it says find the slope of this one at x equals 3. So the derivative gives us a slope, so we'll write find the derivative. First of all, we'll write this as x squared minus 4 to the 1/2. And then we'll take the derivative. Y prime would be, or dy dx, either way, is 1/2 x squared minus 4 to the negative 1/2 times the derivative of the inside, which is 2x. The half and the 2 cancel, so I get x over, for the negative, the square root of x squared minus 4. And so the slope at x equals 3, I'll put 3 in here, and I'll get 3 over 9 minus 4, which is 3 over the square root of 5. That was page 2. Page 3. Find dy dx on this one. This is y cubed minus sine of xy squared equals 3/2. Alright, so we got x's and y's, not easy to solve for the y's, so we have to do this one implicitly. So the derivative of y to the third would be 3y squared dy dx minus, and the derivative of sine is cosine, and that's the big picture here, of xy squared times the derivative of the inside, which happens to be a product. So we got a lot of work here to do yet. So we got the derivative of x, which is 1 times y squared, plus the derivative of the second, which is 2y dy dx times the derivative of the first, x, equals the derivative of 3/2 is 0. Now we have to solve for dy dx. So we have to distribute this to these terms. So I'm going to have 3y squared dy dx minus cosine xy squared times a y squared, and we're going to have it also times a minus, and we're going to have 2y xy cosine of xy squared dy over dx. So now we'll take and add this to the other side and factor dy dx out. So we'll have 3y squared minus 2xy cosine of xy squared. All of that is times dy dx. That's this term and this term. And I'll put this on the other side, which is going to be plus now y squared cosine of xy squared. And if we divide by this quantity on both sides, we get finally dy dx equals y squared cosine xy squared divided by 3y squared minus 2xy cosine of the quantity xy squared. Sand is falling off a conveyor belt on a building a conical pile where the height and the radius are equal. So they're the same. Well, at what rate of change in the radius when the radius is 3 meters if the sand is falling at a quarter cubic meter per hour? So this is a rate problem, so we're going to have to take the derivative of this with respect to time, but first we need a single variable. Well, since r and h are equal, that's our constraint equation, r has to equal h, we can put r in place of here, so we get the volume in this particular case of a cone being 1/3 pi r cubed. And then we take the derivative with respect to time, so dv dt equals 3 times 1/3 is 1 pi r squared, but this is with respect to r, dr dt, and the rate that dv dt is, cubic meters per hour, is 0.25 meters cubed per hour equals pi. They said when the radius is 3 meters, and that quantity is squared. So if I divide by pi and 3 meters squared, or 9 meters squared, That's going to leave just meters per hour. And so we're going to get, I'll just write out 0.25 divided by 9 pi meters per hour. And you can get the decimal for that if you want. Number 9. An open top box is made by cutting small congruent squares at corners out of a 10 by 12 sheet of tin and bending the sides up. How large should the squares cut from the corners be to make the box hold as much as possible? Okay, so we have the paper the tin that's 12 inches by 10 inches, and we're going to cut these squares out of the corner. And they're going to be x by x, and so the volume of this box, which we want to maximize, is going to be 10 minus x minus x, 10 minus 2x times 12 minus 2x times the height x. So, and we want to maximize this, so we want to find the derivative of this, but let's just first do a little bit of multiplication here to make it so we don't have to use the product rule on 3 products. So this would be 10 minus 2x times 12x minus 2x squared, multiplying the x into this. And now I can use the product rule on this and be simpler to do. So dv dx will equal 10 times 12x, derivative of the first, which is negative 2, times the second, plus the derivative of the second, which is 12 minus 4x, times the first. Derivative of the first, negative 2, times the second, plus the derivative of the second, 12 minus 4x squared, times 4 minus 4x times the first. Okay. And then we set that equal to 0, so we're going to have 0 equals negative 24x plus 4x squared plus 120 minus 120 minus 24x minus 440 x plus 8x squared. So I have 12x squareds minus 24 minus 24 minus 40, that's 48 88 minus 88x plus 120, and so let's see, believe at least 4 would come out of this. 3x squared minus 22x plus 30. Not sure that will factor. Let's see if it does. Or I could just use the quadratic formula. So that'd be quadratic formula would be, we're setting this equal to 0. So b would be negative 22. So I'd have 22 plus or minus square root of 22 squared minus 4 times 3 times 30 over 2 times a, which is 6. So that's 22 squared minus 12 times 30 is 124. And so we're going to have the square root of that answer is 11.1. So it didn't factor. So we get 22 plus 11.1 and 22 minus 11.1. 22 plus 11 would be 33 divided by 6 would be about 5, which is too big. I can't take 5 out, so I got to use the 22 minus that number, 11.1355 divided by 6. So I'm going to go 22, subtract that answer, and then divide by 6, and I get 1.81 is how much x has to be to minimize this. So my dimensions would be, of the box, it would be 1.181 inches high, and 10 minus 2 of those. I'm going to store that next so I have it, and so I'm going to go 10 minus 2x, and I get 6.378 or 9 inches is the width, and the length is going to be 8.379 inches. 12 minus 2x. Alright, let's go to the next page. Here we got this, and we're supposed to find f prime. Well, then that would be the derivative of 2x, which is 2. And this is same as 2x plus 3x to the minus 1. So the derivative of 3x minus 1 would be minus 3 over x squared, or 3x to the minus 2. F double prime would be just the derivative of this. And this is similar, was 2 minus 3x to the minus 2. Derivative of that would be positive 2 times 3 is 6, x to the minus 3, which is 6 over x cubed. So we got the first derivative and the second derivative. Show how to use calculus to find the local maximum, minima, determine these points, and use calculus to find the maximum and determine these points. Okay, so we set the first derivative equal to 0 to find max or minimum. So I can multiply through by x squared, and I get 2x squared minus 3 equals 0. 2x squared equals 3x squared equals 3 divided by 2. X equals plus or minus the square root of 1.5. And if I put those back into the original equation, I get 2, I get the square root of 1.5, and I get 2 times the square root of 1.5 plus 3 over the square root of 1.5 as 1 point, and then I get minus the square root of 1.5, comma, minus 2 square root of 1.5 plus 3 over the square root of 1.5. And Those are the points that could be maximum or minimum, and the second derivative, we'd put the square root of 1.5 in there, which is a positive cube. This would be positive, so this is curved up, so this is a minimum. And I put the negative into there, and that would be a negative, so this is a max. Show how to use the calculus to find any inflection points. That would be setting the second derivative equal to 0. 6 over x cubed, set it equal to 0. There's no way that this fraction ever is 0, so there is none. Determine the intervals where f of x is increasing and decreasing. Show how calculus can give you this information. So if this is a minimum, it must be decreasing before that, but we have the interval from negative infinity up to the square root of 1.5. Then we have from there to the asymptote, which is at 0, negative 1.5, and then from negative square root of 1.5 to 0, then from 0 to square root of 1.5, and then from square root of 1.5 to infinity. And if we put something in this interval, we can, into the first derivative, we can find out whether it's increasing or not. The square root of 1.5 is 1.2, so this is negative 1.2, so if I did negative 2, f prime of negative 2 is 2 minus 3 over 4, which is greater than 0, so it's increasing. Something in here would be negative 1, so f of negative 1 would be 2 minus 3 over 1, which is less than 0, negative, so it's decreasing. And then between 0 and 1, square root of 1.5 is 1, and if I put 1 into the derivative, I get 2 minus 3 over 1, which is negative, and so it's less than 0, so it's decreasing. And then over here, something bigger would be like 2, f of 2 would be 2 minus 3 over 4, which is greater than 0, so it's increasing. And f. Determine the intervals where f is concaved up or down. Show how calculus can give this information. So there was no, here, there was no inflection point, so it's always concaved one way or the other, except for we have that asymptote in there, but we can check. So we can check from negative infinity up to 0 by putting something in there, which is negative 1, into the first derivative, and we get 6 over negative 1 cubed, which is negative, so it's concaved down. And then we're going to put something from 0 to infinity, like 1, so that'd be 6 over 1 cubed, which is greater than 0, so it's concaved up. Determine any places where f of x is not differentiable. That would be at the asymptote. Not differentiable at x equals 0 because it is unasymptote. And 11 says sketch this graph with the following characteristics. So it says on the interval from -3 to -1, and then it has something from -1 to 0. So we got this interval, then we got that interval. Then at 0, it's at a height of f is 2. So we got to have that point. And just before that, first derivative is positive, so it's increasing and curved down. And before that, it's increasing and curved up. So it could be something like this. And then on the interval from 0 to 2, it's decreasing and curved down. And then on from 2 to 4, it's decreasing and curved up. And then 4 to 5, it's increasing and curved up. And that's all the further you go. Now, you could have made it come down further here, or less down on either side, but something like that. And that's the sample final.